temperature is our last one. Temperature of a gas solution is not going to have impact. What's going to happen to the gases if you increase temperature? Alright, so they are speedy, high velocity, right? That's all the gas particles are doing. You're not changing the amount or concentrations, nothing. Gas liquid solutions, this is what Nathan was saying, increase in temperature should decrease the concentration of that gas. What is what happens to those gas particles? Same thing. Gas molecules increase in kinetic energy. As they do that, they can escape solution easier. Why? How come that? Why can they do that? Overcome IMFs. Right. Wise words to use. Okay, so if you can overcome your IMFs because you have so much kinetic energy, you can break free of your solvent, you can vaporize, therefore you have decreased solubility. Solid liquid solutions depend, and I have this graph. Well, let me show you. Let me write down my expressions first, or my reactions. This is way back. So sodium bicarbonate in its solid form will dissolve in water in the solution process. So delta H solution means the solution process into Na plus and bicarbonate. And then this is another one I just had to make up. Solid dissolves into 2 ions. If I told you the first one was endothermic, what would happen to the solubility as you increase the temperature?
It increases the solubility.
Why?
Endothermic is not giving off heat. It's so if it's it's absorbing heat, so it's like cold versus hot. Increasing the temperature.
Because of that
The shush, yes. So endothermic means the energy's over here, right? So increasing energy causes what? Right. So shift right. So you increase the solubility because you're going from solid to aqueous. You can even explain it with Le Chatelier's, and you can say it absorbs energy, it takes energy, it's going to cause that forward reaction to occur. But you can also explain it in terms of equilibrium with Chatelier's. So if the first one was endothermic, if I say the second one's exothermic, where's energy? Where? It's a product. So increasing the energy causes a shift left, so decrease solubility. All right, so I could give you information in a chemical formula or equation form, or if this is a solubility curve, explain to me which one is endothermic. Which one? The black line. Why? Because what are these units here? So this is grams per 100 milliliters, or grams of water, and this is temperature. So as you increase the temperature, the solubility increasing means that if the endothermic reaction, once the black one's endo, and then this one right here is exo, because as you increase temperature, the solubility tends to decline. There were a couple of ionic ones that did that, like I think sodium sulfate, and I know potassium nitrate is an exponential increase, but sodium sulfate doesn't really change. Sodium chloride doesn't really change either. So you could explain it via a graphical analysis too. Okay? All right, I think that's it for this. Yes. I'm going to review vapor pressure. Oh no, I did that a lot yesterday. I finished this off with you guys, right? Okay. I'm going to do the rest of Colligative properties, and then we'll do some problems together at the end. Okay, boiling point elevation and freezing point of pressure are next. The properties. I'll let you write down just a little bit, and I'll talk to you. What's the definition of boiling? That's the phase change of boiling. What is it? That's the phase change of boiling. What's the definition of boiling? Vapor pressure equals pressure of the atmosphere. That's important. That's important because that's important to why the explanation behind boiling point elevation. So we learned the first data property yesterday, which was what? Vapor pressure lowering. So what I normally have for a solvent, the solvent will vaporize, at some temperature so much. Have put extra solute in there. Why does it decrease? Why does that vapor pressure decrease? What do you think's happening?
The solute's getting in between the things, so it's harder for them to break apart, I guess, right?
Well, I kind of like that. So the solute, so the surface of my container here, this red is all solvent. Normally it just vaporizes off, it makes sort of vapor pressure. But if I put something else in here, a non-volatile solute, let's call this the black little bitty solute in here. The black solute is interacting with the solvent, right? So there's maybe a little bit more IMF stuff going on. So it's going to limit the vaporization because they just don't. First of all, there's less solvent at the surface. So if you have less surface, then you can't vaporize, right? And then second of all, there could be IMFs at play here that are causing the vapor, the solvents to become attracted to solutes, so it's limiting their vapors. Then we talk about another situation. So this is just the generic vapor pressure lowering. With Raoult's law, we talked about two solvents, but we have to call one of them the solute because it's going to be one that's got lesser mass. So two solvents, both which were volatile, right? So if it was an ideal solution, both solvents would add together their vapor pressures and it would be equal to the total vapor pressure, right? What if they interacted a lot? What if they hung out a lot? What should happen to the vapor pressure total? Decrease. And was that called positive deviation or negative deviation? Negative deviation. So if I have solvent A and solvent B and they like each other, they hang out, their IMFs are strong, they don't vaporize, they have lower vapor pressure than what we calculated with Raoult's law, which was just PA plus PB is equal to P total of solution. So if A and B don't like each other, they prefer to hang out with their own kind. That means they almost repel each other, right? So what would happen with their vapor pressure? And that we call a what? Positive deviation. So Raoult's law explains a lot with mixtures of solvents and solution, or in solutes and solvents. This one's going to be reflecting vapor pressure lowering because it's going to be taking more energy to elevate that vapor pressure. So if this is not vaporizing as much, it's not going to equal the pressure of the atmosphere pushing down. So if it just can't get up to the point where that's equal to the atmospheric pressure, it's not going to boil, right? So what would you have to do to make it boil? I can't change atmospheric pressure. Okay, I'm still in Cox Mill.
Could you increase the pressure of the thing?
How do you increase pressure of a thing?
You have a pressure cooker?
You add more kinetic energy, which is simply by heating it up. So if I have to heat this solvent to a higher temperature to make it boil, I've now created a situation where it's boiling point elevated. Yeah? Does that make sense? So if you know vapor pressure very well, the rest of these are easy peasy in terms of their explanations. Calculations are like regular. We can do this. Okay? So if the boiling point, if it takes more to boil, it's going to be boiling at, so water normally boils at what? 100. It might be boiling at 102 if I add a solute to it. That's limiting the vapor pressure. So how do we raise this? Or how do we calculate this? Delta T is our change in boiling point, or the change in temperature. B is just talking about specifically for the boiling point here. K is a specific constant. It's called the Malal boiling point solvent constant. It's only for the solvent. Okay, do not use that for a solute. What's the lim? Molality. Moles of solute per anybody? Kilograms of solvent. So make sure you identify who the solvent is up front because you need to know that for the K constant. Okay, so after you get your old boiling point, you're going to add that delta T to it to get the new boiling point. And that's how you find out what your new boiling point is after it's been elevated. adding to it because it's been elevated, okay? Second is a freezing point depression. So normally water freezes at 0. If I put salt or something in that water, why would it depress the freezing point?
That's when it gets in the thing, and it stops it from coming together as a solid, so it just stays liquid.
Okay, so there's interference with the crystallization process. Good way to say that one. Okay, so if water particle here and water particle here want to solidify, they need to. How do I solidify?
You freeze it, so you
Okay,
lower
that's
the temperature.
Lowering temperature. So when I'm lowering temperature, what am I actually doing to the molecules?
Lowering the kinetic energy.
All right, so I'm making them go really, really slow. So decreasing the kinetic energy means they're moving really slow. Well, if they're moving really slow, what should start to happen? They should start to what? Attract from their IMFs, right? So they should go by each other and attract and freeze. They should happen all at once. But if there's something in the way, a solute, that limits the interactions, so then you have to make them go super slow. So to make them go super slow, what am I actually doing? Lowering the temperature even more to make them say, "No, what, guys? Like, you've got to attract. So you've got to slow down to the point where I don't care if there's a solute between us, we have to attract." Okay? So that's why the freezing point lowers, because there's things in the way. We need to slow them down even more so that the IMFs come into action. So we need to go even slower, which is even a lower freezing point, to make the IMFs come into that picture here. Does that make sense? I like the first one. Okay, and the same thing, K is our molal freezing point constant for the who? Solvent here, molality, and then for my delta TF there, if I have my freezing point of water as 0 and it's depressed by 2 degrees, what is it? -2. So you're minusing that because you're depressing the constant, or the original freezing point. These molal freezing point and boiling point constants are in your book. If you want to write one of them down, I think water you'll use a lot. This is the boiling point one, 0.512 degrees C per molal. And waters is for freezing point 1.86 degrees C per molal. You'll use those two a lot. You'll use a benzene one, but I think I get to the problem if I need to. You're not expected to memorize them.
So they'll be given on the top.
Yeah, they'll have to give to you. All right, next. Yes. No. Yes. Okay, well, that's not it. Okay. I didn't say this yet. The Van 't Hoff factor. You know, everybody's named something after themselves, right? Scientist Mr. Van 't Hoff discovered that sometimes the freezing point decreased times 2, times 3, times 4 when you put different types of solutes in it. We went over this on yesterday. Sugar or anything covalently bound will usually not dissociate, therefore will have the same one particle before and after the whole dissolution process. So I factor is equal to 1 because it's still one particle. Anything that has the ability to ionize will have an I factor greater than 1. So like aluminum bromide. What does aluminum bromide do?
That's a thing of 4.
An I factor of 4 because you have aluminum bromide, which ionizes into Al3 plus and 3 bromine or bromide. So 1 plus 3 is I factor of 4. So what should they put on their roads to cause a huge depression freezing point? What kind of salt? Everything's a salt. Sodium chloride only has an I factor of 1 though. I mean of 2. Okay, if you put an alkaline earth metal on there, you're still, that's only
Aluminum phosphate.
group 3. So Al, what did you just say?
Aluminum phosphate.
That's only 2. Al3 plus,
What about the?
that's metal and metal. So I'll tell you what they put on the roads. They put calcium chloride on the roads because it has an I factor of 3, and that stuff is cheap. Aluminum bromide is a little bit more expensive, so they don't put that on the roads. Plus, calcium chloride doesn't really disrupt any organisms, because this stuff goes into the environment. So calcium chloride's fine. You need calcium in your body for cellular or muscle contractions and stuff. You need chlorine in your cells for homeostatic, like mucus development and stuff. So aluminum bromide is not the best thing to ingest. So they put calcium chloride on the roads because it's less hazardous, it makes the most ions, which causes the freezing point to depress by 3 times greater than whatever. You can put sugar on the road, but it's only going to decrease it by 1% or 1 time because it only breaks into one, or it stays one compound. So the higher the I factor, the bigger the impact. Okay? Okay. And then I think that's all that says on here. Oh, no, I haven't told you about ion pairing yet. Okay, so what they did was they made all these discoveries about the Van 't Hoff factor, and then they did the experiments, and they thought that the freezing point with sodium chloride would decrease by 2 times 2 factor because it has an I factor of 2. But what can happen with ions? What do they like to do? They like to reform their original compound. So sodium chloride or aluminum bromide, or whatever example is, it can go from here to the ions and then back. So there's not a set where it's like, yes, this is definitely 2 times greater because it stays as the 2 ions. Some of those ions get back together. So it's not simply an average of it, because this simply has an ion or an I factor of 1. This has an I factor of 2. So we would say, okay, half of them go back to the original, would be a 1.5 I factor, but this one actually has a 1.8 I factor due to the process of ion pairing. So on these types of questions, you'll be mainly asked like to explain if the freezing point should have decreased by 4, but it only decreased by 3.8 or something. Then how would you explain that? The ions repaired, causing a slightly insignificant or less significant value decrease. I have a problem for you. Ready? And this is in your lecture notes. It says example 3 and 4. So you don't have to write down the question. What are the freezing point and boiling point of a solution prepared by dissolving 651 grams of ethylene glycol into that much water? Alright, so what do we need here to get the freezing point? Okay, so we need delta T, right? We need, I like to write it as delta T is equal to Chem, because when I worked at James Robb, I replaced the teacher who just left mid-year. She's also left her book and her keys on the table. And her name was Kim, so I taught them colligative properties that next day, so then we made that up together. It was heartfelt. Okay, so here, what's our K referring to? Constant for what? Who is what? Water. Okay, so what's the K freezing point for water? 1.86 degrees C per molal. What is the I for ethylene glycol? Why 1? Right, and another name for this, or another word that you might see in front of this is a non-electrolyte, because what do electrolytes do? Electrolytes should form ions in solution, right? If it's a non-electrolyte, it's not dissolving, it's not ionizing. So I factor should be 1. M is going to be moles of what? Which is what? Ethylene glycol over kilograms of water. Right. Ethylene glycol, 651 grams. Molar mass of that is 62. So 1 mole over 62 grams of ethylene glycol gives me 10.50 moles of ethylene glycol. Yeah. That's the molal constant for water. It's just a constant that you don't have to know. It's just, I just wrote it on the board a minute ago.
Why do we use it as water?
For solvent. The K always refers to the solvent. In this case, you have more of the water, so it's your solvent. Okay? And then kilograms of water is what? 2.5 kilograms. So 10.5 over that gives me 4.1916 molal. So I'm going to plug that in over here. 4.1916 molal. So my delta TFP freezing point is 1.86 times 4.1916, which is 7.796 degrees C. So what's the new freezing point? So take your original, which is 0, minus 7.796, which we can do in our head, right? Negative 7.796 degrees C. Okay, boiling point elevation is, what's the only thing that's different? At what? What else is different? The constant, right? It's not just that. It's not that same thing now. It's a different, totally different constant. This is different. So delta T boiling point is equal to, what's the kBp for water? 0.5512 degrees C per molal. The I is still 1. The M is still 4.1916 molal. Boiling point elevation is 2.15 degrees C. So now what's the new boiling point? 102.15. And they use ethylene glycol as antifreeze. They use it as antifreeze, so in your car, your radiator doesn't overheat. Because most occasions, not even on a hot day, we're not at 102 degrees, right, in North Carolina. So maybe in Texas, I don't know. But if you have a component in your car that would overheat, it would ruin the system, it would ruin the engine, ruin whatever. So if you put solutes in your water, your radiator fluid, then you can actually increase the boiling point of that liquid so it doesn't damage your car. And it's not going to freeze until negative 7.7. Alaska sees that. We don't see that. So we're good. Okay? They have different components for different areas of the nation or world because there's certain areas that exhibit those extreme temperature changes, but we don't. Except for like March this year. So, all right. This is the next question that are we okay there? Yeah. Yeah. 102.15 would be the new boiling point. The next one is one that you would see in a lab-based question on the AP exam. They commonly ask for you to find molar mass with freezing point depression like this. So a solution of 0.85 grams of an organic compound and 100 grams of benzene has a freezing point of 5.16. Determine the molar mass of the solute. Let's write down what we know and then ask me what you don't know, so I know that you know what you're looking for here. So we have 0.85 grams of unknown X. We have 100 grams of benzene formula. And freezing point is at 5.16. So it's telling you that that solution has a freezing point. So is that the new freezing point or the old freezing point?
That's the new one.
It's the new one. So what should you ask me? What was the old one, Miss Imlo? The old one was a 5.5 degrees C. So what can you determine?
It was depressed by 0.34.
I think it's 3, 4. 3, 4.
Is it 3?
Yeah, you didn't even know it. So delta T is 0.34 degrees C. What else do we need to know? For what? For benzene, right. So the K freezing point for benzene is, I don't know off the top of my head, 4.90 degrees C per molal. All right, so what do you guys want to do? Yay! Okay, can you say that loud and proud? Okay. How do you know this? Because you know that you have everything except for molality in your delta T equation. KIM. Plug in everything, solve for molality. If you know the solvent, that's going to go in your denominator. You don't know the moles of solute, and that's what you're looking for. What's the I factor here? Why what? Yeah, it's organic, so you would say, hey, covalent, let's just stick with it. So delta T here was 0.34 degrees C. K is 4.90 degrees C per molal. I is 1. M is something. Moles over what? 0.1000 kilograms of benzene. So your solvent is benzene here. And then solving for X, so how are you going to do this in your calculator?
4 divided by 4.98 and then multiply that by 0.
Right, so 0.34 divided or times by 0.1 be 0.034 divided by 4.9 gives you X equal to, I have this for you, 0.006938 moles of solute X, organic compound X. So then molar mass units are what? Molar mass I was in a restaurant sitting next to somebody, and somebody sneezed or dropped something next to them, and she went, "Oh!" and she spilled her drink. Oh, I was like, thanks. Okay, so how do you get to molar mass from this? Thank you. So the grams that you have originally gave you this many moles, so you're just doing grams per mole, 0.85 grams of X over 0.006938 moles of X to give you 122-ish. Yay! And know what I could do here? I could say, okay, here's the percent composition of X. Percent carbon, percent hydrogen, percent oxygen. You could do combustion analysis with an organic compound. You could figure out the empirical formula and the molecular formula. And then you could do a stoichiometry. You could do balancing equation, determining the volume of gas emitted. Then you could do an equilibrium. Oh yeah, I can see this. Oh, big picture. Okay.
Why would you
I was thinking.
Because he's not a quitter. He's gonna finish this with me. Okay, this is already on your sheet. Look at this with me and then analyze what this occurs, and then we have to do osmotic pressure, and then we're good. Okay, so if I'm doing representing a phase diagram, you know that's this point right here. This red line is what point? So, AKA.
Equilibrium between the solid and liquid.
Okay, but we're talking about colligative properties. So.
Oh wait. Yeah,
But we don't talk about melting and colligative properties.
freezing point?
Freezing point, which is the same as melting point, right? So if I'm depressing the freezing point, how does that look on the graph?
It's gonna go down on the.
When you say down, what do you mean?
I mean in the downward direction.
See, I thought that's what you meant. How would I shift this divide?
Go back to like that's
Here's the freezing point here, right? If I depress that freezing point, which way do I shift this dot? See how this is temperature? To the left, to the left. Okay. Shifting it to the left all the way. Right? So here is a new line that represents depressed freezing point. If the freezing point is depressed, that means you're lowering the temperature at which it freezes, right? If that line represents the point at which it freezes, and this is temperature, you have to shift to a lower temperature value. Shifting this line to a lower temperature value shows me freezing point depression. Then, at some, I don't know, let's call it this one. Let's go 1 atmosphere. That temperature is here. The new temperature is in that little area there. Guess what this value is? Delta T freezing point. Question.
How do you know that red line is be that red line is
Because that's a divide between solid and liquid. Phase diagrams. From last week. Yeah. All right. Now, where's boiling point? Okay, so this blue line is boiling point. Show me the boiling point elevation. Everything goes to the right. And then where's your triple point? So kind of like down here-ish? Okay, that's cool. All right, so the freezing, or the boiling point elevation, where that line is down here. Delta TBP. Cool, right? No. This is like baby phase diagrams. They're big one phase diagrams. They're just like person can't see who's a phase diagram queen. She is. There are some crazy phase diagrams. I'll show you. They don't look like that. Yeah. Yeah. After depression. Well, after the switch is made. All right, and going on to osmotic pressure. Yes. Oh, and then that's what I just did. And then I'm skipping that because that's repeated stuff. Okay, osmotic pressure. I'll let you write down a little bit of pressure, and then I'll show you this video, and then we'll talk. All videos are fun. Once upon a rendezvous. Da 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 da. We had to memorize that. I don't know. read the memorize Canterbury Tales. And do the speech. Yes. Sorry. No, we just had to do the, like, we had to do 12 lines or 16 lines or something. Alright, that pi is not 3.14, people. For last week, no one told me they assumed that. Do not assume it is the same constant as normal pi. This is chemistry pi, not the same pi. Okay? It is not for chemistry. Yes. That is not 3.14, okay? That is what you're solving for. That is the osmotic pressure. I'm going to show you this video. Alright, and we're still videoing. Awesome. We're going to talk about the Canterbury Tales. Okay, I'm going to show you the video first. Can I go forward to show the video? Awesome.
When a solution of higher concentration and a solution of lower concentration are separated by a semi-permeable membrane, one through which solvent molecules can pass but through which solute particles cannot, solvent molecules will pass through the membrane from the side containing the more dilute solution to the side containing the more concentrated solution. This process is called osmosis. Solvent molecules actually move through the membrane in both directions, but because the concentration of the solvent is higher on the right, solvent molecules on the right collide with the membrane more frequently than on the left, resulting in a net flow of solvent from right to left. If we apply pressure to the side containing the more concentrated solution, we can slow or stop the flow of solvent. This is due to the fact that more solvent molecules in the concentrated solution are colliding with the membrane, since the pressure or force per unit area is increasing. The precise amount of pressure necessary to stop the flow of solvent is called the osmotic pressure. A pressure greater than the osmotic pressure will cause solvent molecules to flow from the more concentrated solution to the more dilute solution. This process is called reverse osmosis.
Awesome video, ma'am. Okay, so okay, so pretty much what we're solving for is that osmotic pressure that would require halting, or the pressure required to halt osmosis. Osmosis is the flow of what? Water from high to low, right? So, and this is what that diagram was supposed to show you. The difference in the arms of the YouTube there is going to be equivalent to the pressure needed to halt osmosis. That pressure, I don't know if you remember your eudiometer tubes were like, actually, let me draw the other way. Eudiometer tubes were like you had so much gas up here, and then the gas pressure pushed it all the way down here, and then you had to solve for that H, that height of water, which in the old style barometers, it would be actually already measured in millimeters of mercury. And then we can convert that arm of mercury, that height of mercury, to atmospheres. Remember doing that in gases? So essentially, if this was not, I mean, this is not mercury, this is water probably here, you can convert from millimeters of water using the density of mercury to millimeters of mercury and then convert to pressure. But we're not going to do that. I'm just telling you that's what they would do to calculate that pressure there. In our equations, we're able to use concentration differences because we're biochemists here. So concentration differences, so big M stands for molarity, R stands for, good try, we're doing pressure. 2.1 atmosphere liters per mole K. So R, but since we're talking, this is the gas, that R is like what? I think we've got 3 or 4 R's to work with here. You've got to choose the right one based on the units you need. Since we're doing pressure, then you have to use the pressure one, and I tend to use that one all the time for pressure, atmospheres, liters per mole K. Temperature has to be in Kelvin. What do you think this is going to be recorded in? What did I say pi stands for? Osmotic pressure. Atmospheres, right. So after that, you're done. You can solve for that. How do we actually derive this equation? It's all derived from the ideal gas law. So I'll just show you how to do this real fast. If you don't remember this, I just remember pi mert. So, just like, huh? Oh, pi mart. Oh, instead of like a food mart? Yeah. That would be an awesome pie mart. Okay. I would be a pie mart. Okay, so How do we get to molarity? If you have your pressure here, you need to change your pressure to pi, 'cause that's our osmotic pressure. Divide by volume on both sides. Pi is left. N per V, which is moles per volume, is left. Molarity. Cool? Cool. All right. I have some examples. This is the part that's interesting. So they'll probably apply this in a very biological or like ecological standpoint. So I'm going to talk through some of the applications of this, and then in Reading Guide 5, you'll see a little bit more if you've not already done it. So this is dialysis tubing. Dialysis tubing you probably used in biology with osmosis and diffusion experiments. Dialysis tubing allows for, it's semi-permeable. It lets certain things in and certain things out to go to dynamic equilibrium. So in this experiment here, we've got a flask, and it's got a dialysis membrane there. And as over time the water is coming from the beaker into the flask, you can see the water level, that green stuff, let's call it bile, okay, starts off there. It tends to rise and rise over time, and then eventually it goes to dynamic equilibrium. The pressure it takes to stop that total osmosis is our osmotic pressure, and that's equal to the pressure between, I can't see the difference here again, the difference between the water level on the outside and the level on the inside. So this is the same thing as a U-tube, it's just in a flask. So it's the same thing as this. This is the pressure of the outside beaker water, and it's pushing into, it's coming from the beaker into the flask, and so what's happening is it should be shifting this way and causing this to increase. It's just in a inverted flat or a round bottom flask versus a U-tube here. But that's the process of osmosis, and then simply the pressure to stop would be called osmotic pressure. So it's pretty simple in terms of its definition. And so what happens if I apply more pressure here? Reverse osmosis. Guess where they use that? Where would we want to transfer high concentrations, where would we want to transfer low concentrations of water to high concentrations of water? Why would we want to do that? If we're going to drink it, okay, so you want pure water. So desalination processes in oceanic, I guess distilleries, I don't know what you call them, desalination plants. So in this case, they have a semi-permeable membrane on the grand industrial scale, and they force water from low concentrations of water to high concentrations of water, or just empty tanks. Okay, they're going to force it and extract pure water. From what though? Salt water, right? So low concentrations of water are associated with high concentrations of salts. What do you do? So what happens after all that water is going to remove from the salt water? You have simply salt. Guess what they use that for?
Sea salt.
Okay, so sea salt put on, if it's simple sea salt, it's from the Dead Seas or from the Atlantic Ocean, Pacific Ocean, any of your oceans, you can extract certain salts. You can use it in salt scrubs, in different like beauty products. You can use it in food. You can use it in other processes. But if it's too expensive for you to use, guess what you do with it? They put it right back in the ocean. So now it's in a halo tolerant is what it kind of was called, halophilic environment. Do we experience or live in salt well? What would happen to our cells if we lived in a high salt environment? They would be what? They would dehydrate, so our cells would shrivel up, right? Like little crusty red blood cells, okay? That's not good for us, nor is it good for oceanic organisms. So if the federal government doesn't regulate desalination plants and say, where's your waste going, they tend to put it right back where they found it, which disrupts that ecosystem, which affects the food chains, which affects, it's a domino effect, everything down the road. So that's the ecological application of this, because it does have harm to the local organisms. Another thing that happens is, do you think this process takes energy? Remember active transport, biology? To go against the concentration gradient, you have to apply ATP. Well, that's the same thing, but not ATP. It's just energy in general, which would require us to heat this process up. So at the end, we might have some waste murky water. That wastewater or liquid is hot. They put that into the ocean back as well, because that part's not really all that well regulated. That's called thermal pollution. So thermal pollution can actually denature enzymes within organisms, can cause, less dense water. Is that hot water or cold water? Hot water is less dense water because the particles separate out some. So the hot water would float to the top of the ocean and the cold water would sink to the bottom of the ocean. Then you've got this temperature gradient where some organisms that can live in the, they might need sun, so they have to live at the top because the sun doesn't penetrate the water all that well. So they have to live at the top, and now they're living in a hot environment and they're maybe not used to it. So it causes a lot of extinctions and stuff like that too. Oceanic organisms. I like biology. Okay. Hypertonic, isotonic, hypertonic. Remember this from bio as well?
Yes.
Okay, you don't remember, here we go again. So if you have a hypertonic solution, then that causes whatever your cell or thing inside the solution, it causes that thing to lose water. It causes it to shrivel up. I always remember my brother's really hyper, he's really skinny, so he shrivels up. Okay, so water leaves in a hypertonic solution, making this example as a red blood cell to kind of dehydrate, which can be a bad thing. Okay, so the pressure of the water on the inside has a high osmotic pressure on the inside. It's pushing the water out to the lesser concentrated water solutions on the outside. You can see the information right there below. That process is called crenation. You guys learn this next about crenation? No, okay. Probably hemolysis, because that's more biologically relevant. Because we tend to, you can drink too much water. Too much of a good thing is bad. There can be. This lady who's running a marathon, actually, she tried to keep hydrating herself without hydrating herself with electrolytes as well as water, and she died because she overhydrated. Her cells burst. Bursting cells releases toxins. If your body can't handle those releasing toxins, or release toxins, then you tend to go out of homeostasis and not make it. So, yeah, there's too much of a good thing. Not chocolate, though. There never can be too much. Okay, so I'm trying to get out of that depression mood. Yeah. Yes, it goes in. So I always think hippo gets big, it swells up. Hippo, this is my biology lessons coming out. Did I show you guys my photosynthesis dance?
No.
Okay, I'll find to show you that later. Yeah.
So this is just the movement of water, right?
Not of solutes. There are some solutes that can permeate the membrane because they are so tiny, but we're mainly talking about water. Dialysis tubing is on my next slide. We will talk about solute sleeving as well because that's a fake membrane. It's a synthetic one that's not the same as our plasma membrane. All right, so hypo, it swells up, it can burst. What are we not helping out outside of our cells to limit bursting? So what's on the outside of our cells? Cell wall. Plants have a cell wall, right? So when they take in all that water, they want that water. They don't have any way to move around and say, hey, bartender, I need some water. So they have to store it. Therefore, their cells cannot burst. If they cannot burst, they have this nice turgor pressure that causes them to stand up really straight and firm. If they lose all their water, so if they are in a hypertonic solution, they lose all their water there. That's when they kind of fall over and they're like, please feed me water. And that's when you water them. Okay? So that's what these applications are in the biochemistry realm as well. And then if our cells burst, it's lysing. Lysing means opening up or bursting. So hemo refers to what? Blood. So we're talking about red blood cells bursting here when we say hemolysis, not just any cell. But these are the ones that you're commonly used in examples. What is the purpose of your red blood cell?
To carry blood.
Transport what? Oxygen and what?
Carbon.
You need carbon dioxide to leave, right? So it attracts oxygen to carry to your cells, takes some of the carbon dioxide, brings it back to your lungs, alveoli, out. Okay, and this is my last example of dialysis. So you can see the highlighted line in the middle is a dialysis tubing. So who knows somebody who's had to undergo dialysis treatment? Do you know why they have to undergo dialysis treatment? Their kidneys don't work well enough. Usually it's that people who are diabetics and a lot of organ functions start to fail. So if their kidneys don't work, the purpose of your kidneys are to extract waste from your blood and other lymphatic systems, and it extracts the waste and it puts it into your excretions, right? Because we don't want that. We don't want it in our body. We need to excrete it. So it's like a siphon. It pulls the blood in. It says, okay, you're good. We keep you. You're bad. We put you out. And so that's why you get different colors of different waste and stuff like that too, as the different toxins. So if we have this tubing here, it's semi-permeable as well. These yellow things are our toxins. That's going out into the dialysis waste product. People have to go do this at the hospital. we put that away, and then we keep the red blood cells and then most of our plasma proteins. What's the purpose of plasma proteins? Who's had a cut recently? Scrape. Well, okay, so it's got platelets in it, which are not plasma proteins. I don't think so. I'm thinking fibrinogen. You guys know what fibrinogen does? Anatomy, physiology? Okay. It's a clotting factor. So if you don't have enough fibrinogen, which are those plasma proteins in your blood doesn't clot. What disease do you have? Hemophilia. So people who don't have fibrinogen protein, then they can't clot. That means they are free bleeders and they would bleed. Normal people who don't have hemophilia have those clotting proteins and they'll start to clot pretty readily. You shouldn't be bleeding for very long. But if you don't eat enough vitamin K, then you can't make fibrinogen. So you gotta eat a healthy diet for that. But then you also need your red blood cells, and obviously they're too big to fit through that hole, so they're not permeable to that membrane. And urea, who had urea as their unknown? A couple of us are unknowns. Urea is one of the waste products that we produce, that we get rid of. It flows with the concentration gradient from a high concentration to a low concentration. Because a high concentration at some point is going to be in our blood. We want it to flow to the waste, which should have a low, and we have to work on that some because eventually it starts to get really high in your waste product and low in your blood, so we have to keep removing that urea. Alrighty? Biology lesson over again. And then, haha. Oh, we're cute, man. So this is like the starch and baggie experiment. The starch and the iodine on the outside, what happens when the iodine permeates the bag? Turns brown, black, kind of the iodine and starch mixture. Okay. Have to make you laugh. Okay, you guys have your problem set in front of you. Actually, for your split your properties, there's 5 of them. We have 18 minutes. Yes, we need to split up the problem first here. They're underneath the 1 through 13, which is your noun later problem set. Go ahead and find those for me. It should be on the second page of the notes I can pick. So the first page was your notes. The second page is where the problem set is, the properties. There's only 5 questions. So right here is the last question, number 13 on the noun later problem set, and then right under it are 5 related property questions. I have the answers for you if you want to write them down. I typed these up until first period today. Oh,